Professor Belfrost's science class is back.
Hi, welcome back to this channel. And today we'll again discuss another concepts related to science. So here's the science tutorial for you today. Are you ready? Let's continue playing this video. My face on this can be heard. Okay, I can hear my sound now. My audio system sometimes working. Okay, so normal tension and other examples of forces. We continue our last lesson. Normal tension and other example of forces. So forces are given many names, okay, for their respective function. So push, pull, thrust, lift, weight, friction, and tension. Okay. So there are several groups. For example, first one, normal force. Okay. So weight is a pervasive force that acts at all time must be counteracted, right, to keep an object from falling. So, I mean the supportive force, okay, to support this weight, okay, and this is the normal force, okay. You see, weight, normal force, okay. If we don't support it with your hand, we need a normal force. For example, you put it on the table, the normal force is acting on the um, system, okay. So we must conclude that whatever supports a load, be it animate or not, must apply an upward force equal to the weight of a load, as we assumed in a few of previous examples. And if the force supporting a load is perpendicular to the surface of the contact between the load and the support is and its support, that is what is called normal force, and given the symbol N. Okay, normal means perpendicular to a surface. Okay, so let's dive into example. Weight on an incline, a two-dimensional problem. So we have a skier and a slope. So her mass, including the equipment that she used, is 60 kilograms. So first question, what is her acceleration if friction is negligible? And the second question, the second point, what is her acceleration if friction is known to be 45 newtons? Okay. So first one, actually you need to separate it into the respective horizontal and vertical component. This is what we have done in the previous chapter, right? So because weight is in this direction, the normal direction is in this direction. Okay, this and this is not um, a force that we can calculate easily because it has no, we have not normalized it. Okay, so weight need to be normalized into its the respective horizontal and uh, vertical component. Okay, you see W perpendicular and W, this is horizontal. Okay, see, so acceleration is on the horizontal side. It means from this part, this is cosine, this is sine, right? The horizontal one is sine. So weight sine 25 degree divided by m, you can get the acceleration on the horizontal. And yeah, the F net, if we include friction, we not consider the weight is contracted by friction. So it's like this, mg sin 25 minus F divided by m, and it gives us a little less acceleration, which is 3.39 meter per second square. And this is the section that explain how to resolve weight into the components. Okay, so pay attention that this is just one possibility. Yeah, sometimes the theta can be placed here, sometimes the theta can be placed here. So you need to adjust it to the question requirement. Okay, the important thing is that you understand trigonometry. Yeah, to the most basic concept, so you don't confuse which one is sine, which one is cosine. Okay, because that's really easy. Okay, I want you to pay your 1 or 2 minutes. Okay, okay, to read this session. I think this is self-explanatory. Okay, good. Now we've moved to the second force, which is tension. So a tension is a force along the length of a medium, especially a force carried by a flexible medium such as a rod or cable. Okay, so tension comes from a Latin word, means to stretch. Okay, so for example, we have a tension in a rope. Okay, you see, so this is tension, this is weight, so they are both opposite in the direction, right? And if the acceleration is 0, then t minus w equals 0, and the weight is suspended. And the t equals w equals mg. Okay, let's dive into the example. Calculate the tension in the wire supporting a 70-kilogram tightrope walker shown in figure. So you see, her leg may be he or she. Say that this is a male, so his leg is pressing down the rope, so there a weight applied here, and the tension is not working only horizontally or vertically, but it creates certain angle. Okay, it means that it has vertical and horizontal component. Okay, you see here, the wire is not perfectly horizontal and it cannot be, but is bent under the person weight. Okay, so and also there are two tensions, the left tension and the right tension. Okay, the left tension and the right tension of the horizontal will cancel each other, so we are only left with the vertical tension, and then we add. Okay, and tension of the left and right must be the same, right? So we can find out the tension, and we just input it, and we know that the tension on the vertical is TLY, left y plus right y minus the weight. The TLY is just TL times sine 5. Okay, and also that is the same with TRY. And yeah, by following the step that is shown in this book, I think this is very clear, and you get that the tension of the rope is 3,900. If we wish to create a very large tension, then all we have to do is exert a force perpendicular to a flexible connector. For example, this is shown in figure 4.18. You see? Perpendicular. Okay. We saw that the tension in the rope related to the weight of the tightrope walker in the following way. So T equals W over 2 sine theta. I mean from this part. Okay? This T from this example equals W over 2 sine theta. This is the general formula. Okay, and the W can be substituted with any perpendicular force. Okay, and this can be used to analyze the problem of sagging. Okay, now let's discuss also another important topics, which is related forces and initial frames. So there is another distinction among forces in addition to the type that already mentioned above. That some forces are real, whereas others not. And real forces are those that have some physical origins, such as a gravitational pull. But contrastingly, the fictions forces are those that arise simply because an observer is in an accelerating frame of reference, such that they rotate or undergoes linear acceleration. Okay. So an inertial frame of reference is one in which all forces are real, and equivalent one in which Newton's law have the simple form given before. And Earth's rotation is slow enough that Earth can be nearly considered as an inertial frame. The crucial factor in determining whether a frame of reference is inertial is whether it accelerates or rotates relative to a non-inertial frame. Okay, now let's learn some about problem solving strategies. Step 1. Once it is determined that Newton's law of motion are involved, it is particularly important to draw a careful sketch of the situation. I mean the free body diagram. For example, like this. Okay, this is Tarzan maybe. Okay, so we see the tension. There's the force that is pulling the rope, and this is the weight of the Tarzan. Number 2, identify what needs to be determined and what is known or can be inferred from the problem as stated, and carefully determine the system of interest. Okay, because we only need to input the forces that needed. Okay, not all the forces, because it will confuse you. So a diagram showing the system of interest and all the external forces is called a free body diagram. Step 3. Once a free body diagram is drawn, that Newton's second law can be applied to solve problem. If the problem is one-dimensional, that is, if all forces are parallel, then they act like scalars. But if the problem is two-dimensional, they must be broken into a pair of one-dimensional problems. Okay, by projecting the force vector onto a set of axes chosen for convenience. How about if the three-dimensional? We'll later, maybe not in this book. This is just basic discussion. But if there are three dimensions, it means you have to separate into three axes, right? X, Y, and Z. Okay, so this is also very important. Step 4. Check the solution to see whether it is reasonable. In some cases, this may be obvious, but yeah, in practice, intuition develops gradually through problem solving, and with experience, it becomes progressively easier to judge whether your answer is reasonable or not. Now let's see further application of Newton's law of motion by solving the example. Suppose two tugboats push on a barge at different angles shown in the figure below. That the first tugboat exerts a force of 2.7 times 10 to the 5 Newton in the x direction. The second tugboat exerts a force of 3.6 times 10 to the 5 newtons in the y direction. If the mass of barge is 5.0 times 10 to the 6 kilograms and its acceleration observed to be 7.5 times 10 to the minus 2 meters second square in the direction shown, what is the drag force of the water on the barge resisting the motion? Okay, you see the force applied, the total force that applied on the barge is Fx and Fy. Okay, they are horizontal and vertical force. I mean when we see it like this. Okay, so we first need to know the total force in magnitude by taking Pythagoras, and also the angle need to be calculated by using arctangen. Then we can calculate the net force by subtracting with the drag force, and we can obtain the drag force because we have known the acceleration in this way and the mass. Okay, see. Next example. Consider the traffic light mass 15 kilowatts suspended from two wires as shown. That find the tension in each wire, neglecting the masses of the wire. Okay, actually this is also not very difficult, but you need to see that this time the tension of both sides not equal to each other because they have different angle. The first one is 30 degree, the second one is 45 degree, so it's not equally distributed. Okay. But the net horizontal force must be 0, so T1x equals minus T2x, but the tension is different, will be different later. Okay, so T1 cos 30 equals T2 cos 30. It gives us that T2 is greater than T1 by this factor, and you can see T1y plus T2y minus W equals 0 because it is in resting position. Okay, it doesn't move on vertical axis. So T1 sine 30 degree plus T2 sine 45 degree equals W, and you can calculate like this. What does the bathroom scale read in an elevator? For example, you see this figure. It shows a 75 kilogram man, weight of about 165 pounds, standing on a bathroom scale in an elevator. They calculate the scale rate. The elevator accelerates upward at a rate of 1.2 meters per second square, and if the elevator moves upward at a constant speed at 1 meter per second, it means that it has no acceleration. If it has no acceleration, then the weight must be the same as the normal force. It means that the scale will show the weight of the man, okay, which is if we take 75 times 9.8. Okay, but if it accelerates, okay, it means that this is not a true force longer. Okay, you see the force has increased, and it gives us 825 newtons. Okay, if it is accelerating downwards, then the weight will be less on the scale. Okay, if it's accelerating upward, the scale reading will be greater. If there is no acceleration, the scale will show the weight as it is. Okay, and if it is free falling, then the reading will become 0, or it will appear to be weightless. Okay, I think we are until this in this video. Okay, before I end this video, I want to share another good quote for you. Vince Lombardi once said, "In great attempts, it is glorious even to fail." That's the end of the video for today. Thanks for watching, thanks for following so far, and here's what you need to do. Please subscribe, give a thumbs up, comment, and share this video to your friend. And also, don't forget to check our website at https://science-exploits.unaux.com, and I'll be back on every Tuesday, so keep watching and be thoughtful. Goodbye, see you.